Como é que você vai saber se o som está tocando ou não, Sal? Okay. Hello, everybody. Thank you again for coming for our last session of the deep learning course given by Matthieu, who's leaving on Thursday. So this is the last session and the last week we are having Matthieu here. So Matthieu, thank you again for teaching us how to do deep learning and giving this primer course for us. And I thank again the public that we have here, the public we have here with us. And I thank again the public who is following us in the web, online. And when we will have the archives open, are the archives already open, Mikhail? The PDFs are open, the YouTube videos are open? Not yet, but very soon, I hope. Yes, very soon. So very soon, the PDFs are already open, the YouTube videos are already open, so you'll be able to send the links to your friends or family. Okay. Again, I ask you to follow us at our Twitter or our blog. Our Twitter handle is RecordBR, so it's written here, RecordBR. Follow us at our Twitter or our Facebook, is also RecordBR, where you will be aware of the animations that we'll have very soon on other interesting subjects, other machine learning subjects, computer vision, etc., including deep learning. So, Matthieu, thank you again for this course, and I give you the mic.
Thank you, Eduardo. It's my pleasure to be here. Thank you to be still here after 3 hard courses on deep learning. And so today, this is the last course, so we are going to change the way to proceed, because Mikhail will start now, and I will close the session after, right?
Okay, so last week we had a challenge. Anybody here managed to finish the challenge? Nobody? Okay, that's interesting. Okay, so we're gonna see very shortly a plan for the solution. But before that, I'd like to remember you that in the first class, we had some tricks for training big networks like ImageNet and things like that. So we had first order optimizations. In the second course, we have seen some tricks for transfer learning. In the third course, it was the challenge itself and platforms for transfer learning and for deep learning. So today we're gonna just take a quick look at this, which are some tricks as well for ImageNet. So if you are planning to do a deep neural network, to train a deep neural network, you might want to know this. So here I've just listed some of the conclusions of this paper. So this is a very interesting paper. You might want to choose to take a look at it. And their conclusions are just for ImageNet. So they have trained a neural network on ImageNet, and they have varied a lot of parameters to see what's the impact of those parameters. So for example, they have noticed that other color spaces are better than RGB. So there are other color spaces that work a lot better, and they managed to get nearly 6% better score with other color spaces. So this is the kind of thing that you must know if you want to win a big competition. So if you want to take a look at this paper, this is might interest you. Okay. The PDFs are going to be available online, so if you don't want to take notes, or if you want, you can too. This is the correct thing to note here. All right. So going back to the challenge, if you remember correctly, the challenge last week was to do a transfer learning task on Pascal VOC, which is a data set. And this was the challenge I gave you. So it was to reproduce the result O from the devil in the details, which is a paper. And the results are 79% on Pascal VOC. Okay. So if you don't want to do something very big, if you don't want to cross-validate your C and lots of stuff for the SVM, you can easily get to 70%. So anything above 70% is acceptable. Anybody here got 70% at least? No? Okay, so nobody? Let's just see what are the steps for this task. So the first step is feature extraction. And for feature extraction, we have seen an example last week. So we had MATLAB here. And with MATLAB, we had described 2 cat images and 1 pepper image. You remember that? Yeah? So here for this task, all you had to do is repeat this step for every image in the Pascal VOC dataset. After that, you could train a linear SVM like they have trained a linear SVM. It wasn't a radial basis function. It was a linear SVM. And then we have here the first question. What about C? What do we do about C? Anybody have an idea? Because C is a hyperparameter of linear SVM. And here, if we want to get good performance, we have to choose the best C. And what are the strategies to do that? It's a question. Yeah, grid search. So grid search is an option. Anybody else? Random search? Yeah, it's possible. Yeah, it's possible. Yeah. No? Okay. So we have lots of things we can do here. There are lots of optimizations that are better than grid search, and we can do that. I'm going to leave this to you so you can go after it. But a simple thing we can do is to fix the C. So if you want to train quickly a model to see how it's going, you can fix the C and see how it goes. Of course, the C is going to affect the results. So a better C is going to give us better results and so on. After we have the linear SVM training, we have this type of classification. So all the images from the test data set, we're going to give them to the network and ask what's the correct label for them. So the network is going to take a decision here. And after we have this decision, the labels, we're going to calculate the mean average precision. And the mean average precision is calculated with the labels we get here and the ground truth, which is the correct labels. Okay? So for this, I was expecting somehow people to get to a result like this. So this is just oh, it doesn't work, okay. I'm gonna change quickly the color scheme. No, It's better. You can see, no? Yeah, you can see? Everybody can see that? Like this, you can see? Yeah. So here we have the describe function. This here is just things you do not have to do. Okay, so this is the downloading the model, downloading the program, etc. And here's the part we have seen last week. So this is just the description, and we are saving the description. Here's the same thing, but here we are doing for a single file, and here we are doing for multiple files for a folder. Okay, and after that, you are done. So this is just the description. And for the training, it's something very simple, but we have to have here a function to calculate the MAP, the average precision here. So this is, we can ignore this for now as well. And here we're gonna have a simple code just to train a model. And this is the part where we are interested in, training the model. So we built the set, we train the model, we test the model, and that's it. So very short codes, very simple, okay? You don't have to memorize all that, just to show, okay? So this was an expected solution. You can now try that at home, maybe. The source code will be available online as well. So in the YouTube link or in the CIS chapter webpage, you can find the code later. And that's it for the first day, the last day, sorry. And I'm gonna pass to Matthieu now. So answering this last question, no, it's not the end because we switched. I'm the first now. So it's gonna go to him, and have a nice class.
No question? I think it's clear.
Yeah? Okay, so the question is, how long did it take to extract all the features? Is that? Okay, so the feature extraction actually is kind of faster than the classification itself. The feature extraction is gonna take about 30 minutes, maybe, to extract all the features. That depends heavily on your computer, so if you have a better computer, you're gonna do it faster. I did it in my laptop, so not that fast. And after that, for training the classifier, maybe another 30 minutes, 40 minutes, so not a lot of time. Any other question? You can ask any questions here regarding any of these steps, feature extraction, linear SVM training. Yeah? Yeah? Yeah. Backpropagation to find C. Okay, if you plug an SVM at the end and you manage to get the loss of the SVM, maybe you can backpropagate the loss through the network, but that's very hard. So it's gonna take a while to do that. You're gonna have to do some work to propagate this loss. But out of the box, I don't think there is something to get the loss of the SVM and propagate back. Do you know anything, Matthieu? Lasagne has that? Okay, so. Yeah, actually, you can plug anything at the end. You don't have to do an SVM. Here we use an SVM because in the paper they are using an SVM, but you can create a new network at the end. So you might have two networks, one for feature extraction, another for classification. And with another network, it's very easy to get the loss. So because you have that already, you have the backpropagation.
Usually people, already did this kind of experiment and find that the linear SVM on the top for this kind of small data set, even if you extract deep feature before, is one of the best, for doing the classification for this kind of small data set. Okay, because otherwise, of course, you can just consider like you have a deep and you just add the last layer of the deep with random parameter that you are going to learn, exactly as Michael said in the course about transfer. This is, the basic way to do transfer is just to cut the head and to put a new net or new layer for the net, the classification on the top, and try to backpropagate in 2 steps or with 2 different learning rates and so on. Okay.
No? Okay. I have no questions then. We're going to switch the computer, so it's going to take 3 minutes maybe? Not so much.
Thank you. Worked, everything? The video? Okay, right. So we're going to continue and to finish this course. So just to remember that it was in the context of this deep learning chair that I'm here for 2 months, ending this week, here on Thursday, to work typically on deep learning with Professor Eduardo Valle and all the team here, right? So the point for today is to see, yes, a little bit to summarize the things about transfer and what about beyond ImageNet, and in particular, how to get things more complicated than just keyword for one image or things like that. So to see how we can interact between visual information and textual information, okay? So just to remember, so what we have seen with the transfer, ending today also by the demo and the test proposed and by Michael. So it's really, I mean, one of the things is that from ImageNet, we can just take the features, and we are going to see also many things about that during this course, and use these things as generic feature for other things than for doing just ImageNet classification with the 1,000 classes that we have in ImageNet, right? So I presented, for instance, things about retrieval last courses on Friday. And there are many different things to do in a nice way, different kind of transfer from this data and from this learning from ImageNet to other kind of targeted data sets, right? So one point that is very important also to have in mind when we are talking about going out of ImageNet to other kind of data set is that globally ImageNet has centered object, okay? And most of the time, I mean, in the real application, or what, we do not have this kind of well-prepared object, right? So that have been pointed out by researchers as efforts, for instance, at the beginning of this success of ImageNet, okay? But we have to say that there are plenty way to exploit the ImageNet data set and learning, deep learning that we can do in other contexts, right? So when I was here, I have presented things about that. So typically how to adapt ImageNet or deep learning or deep CNN strategy to this kind of data set that can be, for instance, Pascal VOC or MIT indoor or 15 scene, COCO dataset, and so on, that have many different objects. When you have an object, for instance, a car, it can be, for instance, many cars, and it can be small, not well centered, and so on. Okay, with clutter, many things like that. And so I have presented during my seminar, research seminar. I mean, I made the first part of my visit here. Different things to deal with this kind of problem, right? So I'm not going to, of course, to redo. So I just point you and invite you to see. I mean, the PDF are online already about there's approaches that basically that one of the main idea I'm going to develop also today in other contexts is that if you have no more one object well centered, the idea is certainly, I mean, to be able to have a larger CNN where some part of the CNN will be able to focus on the correct regions. So that means typically on the regions of the car here, I will get a decision by identifying where is my images inside my my car inside my within my image, right? So the difference with the typical large VGG, for instance, that I presented during the second lesson is just that it's like a larger VGG, all right? So the one VGG would be in a dot line here, okay? And the idea is that one VGG may focus on one part of the image, and then for a larger image, I will have to move around the VGG, so to have this kind of parsing the whole image with different VGG, okay? And then I will get as many answers as I am able to move around, okay? So that means if I move on a grid, for instance, of 10 by 10 in my whole image, I will get 10 by 10 answer of having or not a car inside my image, right? Okay. And interestingly, this is related to other topics. Of course, that is typically the detection, where you are no more interested in just knowing if there is, I don't know, like people, for instance, or a car in your image, but you are really interested in being able to extract, so to detect and to localize the object, right? So again, people after 2012 did that by using the deep CNN, right? Pre-trained on ImageNet and fine-tuned on the problem. So one of the main techniques that have been developed to do that is what we call the region CNN or the RCNN, right? And how it works is like you have your input image, and then you have a first tape that is independent from the CNN part coming after, where you just propose many bounding boxes that can be candidate to be, for instance, to have a people inside, right? So this things is related to having or to detect silent region, right? Silent regions into your image, where you consider that after you forget the input image, you just focused on these regions, okay? That can be, for instance, 2,000 of image of sub-images if you want, right? Okay, so you have this kind of process that is mostly based on segmentation, hierarchical segmentation, without learning in the first version, but of course, after many people developed also some bounding boxes extraction that may contain some learning also, of course. But basically, the idea is that from that image, I will have like, for instance, 100 of bounding boxes, okay, that may contain my object. And then each of these bounding boxes are going to pass through the big CNN, right? And as it is not to do classification for ImageNet, you also have to adapt, of course, the head of your CNN, mostly as presented for the transfer, and then you adapt to the classes that you have in your target classes, for instance, for Pascal VOC, right? And you retrain this part, and after, in test, you arrive with the test image, automatic extraction of candidates. Each candidate pass through your net adapted to produce a classification on the target classes, right? And you get an answer for each of your sub-window, having or not, or being or not a people, or whatever you have here, an aeroplane, a TV monitor, and so on, right? Okay. So that approach was so successful, okay, for communities that, of course, there are at least two improvements proposed by the same authors. That was last year, actually, one in ICCV and one in NIPS. Okay, so the most famous conference is in vision and computer vision and in deep learning, machine learning, right? So, but basically the idea was just to go faster. Of course, that was one point first, and typically to apply the same kind of things I explained here, where instead of me doing all the computation for each sub-window independently, for one to another and so on here, okay? You can integrate all the things by doing like your, no. Okay, it's a problem? It's okay? You don't care. No, we have to see that, not my face, okay? Right. Right, so, okay, so then you can put all the convolutional layer into one computation for the whole image, and then for each sub window, you just have to find where it is, okay, inside the whole things, and then apply the rest of the process thanks to that and the learning inside that and so on. Okay, so that was one of the improvements, and of course the other one was to get a more accurate window at the end, because it's a detection task. So you want to be able to have a very fine window for each of the objects that you have in the image, and you can also refine this at the end of the deep learning strategy architecture, right? And so this is also very interesting things that we observed recently with deep learning and deep CNN strategy, is the ability to actually to get like two different outputs, right? That are more or less that share some part of the net, and that have two different outputs, right? So they have some parameter here to be able to really find the correct classes, right? That they do not share, of course, with the bounding box regression, that we give you a very accurate boxes corresponding to your object, but them together, they share a part of the net before, okay? And so, of course, they help together for having a nicer updating of many parameters before being splitting in two parts, right? Okay, so this is another extension of ImageNet classification, all right? So first transfer, second detection, And the third one, very important, of course, is the extension to segmentation. So when we are here, or when we talk about, of course, this kind of approach, we are not so far of producing some location of the object. With detection is a location with a bounding box, okay? So certainly the next step, of course, is to produce this detection with a segmentation of each of the objects, right? So how it works, just to remember that the segmentation is you provide one image and you expect to have this kind of output. So that means for each pixel, you are able to give a label, right? And you want to be able to really, segment the different objects that you have in your scene, right? So this is typically when you have this kind of information during the training. This is a fully supervised segmentation, right? So you have all the label for all the pixels for any images that you use on supervision. So how to adapt or how to use your deep to get a better segmentation, right? So exactly as I presented before, you have a large image, and what you can do is like you have a small, a very deep and very nice deep, but applied to a subpart, and you pass. So you go through the whole image with your deep, okay, and you can see that exactly as a larger deep with all the convolution inside, and of course a larger decision that contain the map actually. With the location of the different decision for each of the pixel, or somehow not of course all the pixel, but a subset. I mean, because the resolution is going down. Okay, so usually it's not full resolution at the input image, but of course is more than 1 by 1. Okay, so the size you have here tell you something about the location. It's not clear on the score that you have. And typically here it's like I extend a heat map. So one of the slice that I have here for one of the class, right? That could be, the answer of having a tabby cat, here, right? And so the resolution is not as good as, of course, the input one, but it depends on the grid, how it works, how your deep is going to subsample the spatial resolution, okay, during the process. Basically, you can define some deep that do not subsample too much and so on. But the idea here was to use really, a pre-trained deep. Typically, like a VGG, I want to take my VGG, I want not to retrain, I want to get and to take advantage of this VGG, very beautiful VGG pre-trained on ImageNet, right? So I have the constraint of VGG that then sample images and so on, right? Okay, but still I am able to do that. I can consider also upsampling, right? In a different way to do that, of course. So here it's the same thing with the input image. So I apply my deep convolution network adapted, and of course I can learn that with my segmentation mask. That is very important, and then I can fine-tune my convolution with the segmentation mask, giving an answer for each of the pixels of the image. For each of the classes I have in my target problem, right? And then from that, okay, I re-extend to get using a bilinear interpolation in that case, okay, to be able to have a heat map corresponding to each of the pixels of my input image, right? And of course, here to get the final segmentation, what people do propose here is to use like a classical CRF optimization in order to be able to refine, I mean, like this first map, okay? And more specifically, I mean, we can exploit this map in the parameter of the CRF in order to get a very efficient and nice segmentation at the end, right? Okay, so like again, just more refined than detection, okay, segmentation, you take care about the information for each pixel by using this the kind of very well-known CRF optimization for segmentation, right? And yeah, the other technique I was putting like in a highlight for this kind of technique is to do the same kind of thing. I mean, just to be able to undo, I mean, all the pooling and the trace in a dip also. So I put like a deconvolutional network after my convolutional network that converge here. And of course, there is, I have to put many links in the unpooling corresponding to the type of pooling I made here, okay? So when I say that I do a max pooling, I keep the information of who was the winner and where was the winner inside my max pooling window, okay? And this winner, I keep the information to get back for the unpooling after, right? So it's not the same thing as Fergus proposed, for instance. I show it in my first lesson, my first course on deconvolutional neural net to see, I mean, try to see what's going on inside the convolutional neural net. Because here, and it was not the case for Fergus, you learn, I mean, you try to learn, I mean, different convolutional, even if it, I mean, different filters. You also learn these filters here in order to get the best segmentation mask at the end. Okay, so of course, Fergus didn't have this the information and didn't want to of course, to learn a segmentation mask. So the objective is different, right? And we can see the kind of answer that we obtain progressively here, right? Typically on one example. So I think it was a bicycle because I see bicycle after. But typically this can be what we obtain in again in a slice here, certainly corresponding to perhaps to the bicycle detection, all right? And then when you unpool, so you see that the image is bigger because, I mean, each pixel is now smaller, right? Okay, and you see how the things are extend from 1 to 4 here, and we keep the information where the pooling was coming in the other side. Okay, so if in this side it was that one that win when I reduce, I keep this information, and when I need again to extend, I will propagate this value to the one that has been used for the decision on the other side. Okay, so this is the way that you unpool. So nothing that just keeping this information and putting this information here. But after here, the very interesting thing is that we filter. So we have a filtering of that, and we try to learn filter that will give me step by step the more accurate segmentation map corresponding to my bicycle, I would say, right? Okay, so this is typically not exactly, of course, the same strategy, but typically the kind of strategy that we can find when we are doing segmentation with deep, right? With a deep approach. So, of course, it's for full supervision. And yes, it costs a lot, I mean, to segment very, I mean, accurately each of this kind of images. So people also consider that perhaps we can work or try to work in a weakly supervised way. So that means instead of, okay, really, I mean, accurately drawing each of the image or each of the region inside the image, okay, we can consider that perhaps with more tricky, of course, machine learning techniques, being able to handle with images that are just labeling at the image level. Okay, so that means, okay, I'm going to pass through the whole set of classes I may have in my data set. Okay, and for each image, I'm going just to say, okay, of course, I have a any background, like chair and table here, for instance, right? And of course, in that case, it's more scalable for large number of category and certainly large number of images that we can label, right? Right. So in that case, of course, when we consider a standard supervised learning technique, we have to we have the map of segmentation, right? And in that case, we don't, right? So I just mentioned here two techniques, and just to show you that it's a very, very recent work, because all the things I'm talking about are, of course, is in between 2013 and today, okay, I would say. And let's say how it can work. I just put one slide on the first method, I think, yeah. Okay, so the point when you are in a weakly supervised way is that the mask that we, if I come back to that, for instance, the mask that we have for the learning, during the learning here, to learn the convolutional net, for instance, or here, the mask that we have during the learning, okay, in order to learn the different parameters of the model, we don't have it anymore. We just have the labels, okay? So basically the technique is proposed to say, okay, I just have the label for one image. I can consider that I have my deep, right, learning that is able to produce some labels, okay? Certainly they are not perfect, but I can have like a loop. So considering that they are not so bad, I can use the score maps actually and to produce segmentation maps, right? But of course, with biasing them, okay, with the real labels that I know them during the learning, right, at the image level, right? Okay, so that means that I am like, if I was in test, so I produce some maps, okay, and I'm going to use the score maps and plus the whole category actually to remove all the different categories that can be here in that image, and to be able then to produce sorry, a very good background localization. And then here, well, we don't see very well, but we have like a segmentation map with the 3 or 4 objects corresponding to these labels, of course, and induced by this deep map. Okay? And of course, the good thing we don't see so in this slide, I don't know why, but it's not correct, the arrow, that, okay, with this map, I come back to the loss, of course, of the deep. Okay? So as soon as I can produce that, I can say, okay, then I can refine exactly as before in a fully segmentation framework, okay, my deep neural net, right? So I'm going to refine, and then I iterate the process, okay, thanks to that, right? And then I will produce a fully, learning, I will be able to learn exactly as before, my deep CNN, and then I can do my segmentation as I presented with the CRF or that kind of things before, right? Okay. All right, and so for some of you that was not in my seminar presentation, so this kind of techniques I just presented before are able to produce like amazing results on many different images. So typically this have been produced by the Facebook team of Luca and presented for one of the most important segmentation competition, which is the Coco one on the Coco dataset, I would say, right? Okay, and so there are few examples like that. Okay, where you can produce very accurate answers, but it's also sometimes for many different kind of objects and with a lot of regions with different things. Of course, there are many errors. Don't trust all the labels that are produced here, but they're quite good. Okay. All right, and so this is for segmentation, and then it's still like very visual oriented. Okay, so I'm keeping the very simple keywords information as textual information, right? And now we are going to see yes, essentially one, but I will finish by discussing on one slide this kind of things, but then to switch to this part of learning multimodal. Okay, so it's more or less exactly the following of my course on metric learning. Actually, I finished by this slide just to show. No problem. It's okay. Right. So where I finished my course on evoking this slide of having no more only image that we have to put together in order to get a better similarity. So try to learn a better similarity or better space for representing only images, okay? But what happened when we try to put together images and text in a common space, right? In a joint space, having this kind of semantic, fully semantic information represented, right? So we will see different things. I will not really, go into the detail. Sometimes it can be, for the beginning, visual bag of word. It can be, of course, even some CNN, deep CNN, okay, whatever. And for the text representation, at the beginning, we will see also bag of word because it's come from that. So it's a vectorial representation, TF-IDF, or more recent embedding into a vectorial representation for each of the words, like word2vect or compositional embeddings and whatever, okay? But to start, the point is really, like, is it possible to align both representation? Okay? For, of course, similar pairs. Right, so what can be the images before going into the kind of techniques? So it can be exactly as, for instance, for each one pair is one image and, for instance, 2, 3, 4 keywords. So it's already more than one keyword, okay? Or it can be a sentence, or it can be a caption. Okay, a real caption, so few sentences for each of the image, right? Okay, so this data set, typically Flickr 8K and Flickr 30K, and also a COCO subset also will be, used for the evaluation of this kind of techniques, right? Okay, so how to do that? The first thing is to come back to start at the beginning. So typically this is a very old technique about putting things that are not coming together, being of different content or coming with different sensors or whatever. It's to have this kind of canonical correlation analysis that is not very new, as you can see, right? And this is basically the idea is that you have two vectors in two spaces, and you want to define two transformation for each of them to go into a common space, right? So it's a linear transformation in that case because you try to have a matrix to pass through the first space to the target space, okay? And a second matrix to pass from the second space also to the target space, right? And you try to do what? To do that when you do this transformation over each pair, okay, you will have a correlation in between the two outputs. So your image in the new space and the text information in the new space, that will be on your data set as the most correlated, right? So you try, that was the criterion. It was like to find here like a vector pair that will transform you and put the output from the first space in the common space and the second space, okay? The correlation of that, okay, maximize over, of course, the whole set of transformation that you consider, right? Okay, so there are if you see exactly the criterion of that, if you consider your data at the beginning as a random variable, you will have exactly, the correlation criteria that may be written like that, okay, with the expectation. And then you can rearrange, of course, the computation because only the expectation over the data are significant here. There is no expectation over the parameter, of course. Okay, and then usually you have a way to estimate in an empirical way the expectation over your data, and then you are able to optimize. Okay, so to maximize this criteria over all the W1 and 2 that you have to transform. To pass from your first image space to the joint space and to the second text space to the joint space also, being sure that this will be maximized, right? There are to solve this optimization function, there are two methods, one iterative method and one global optimization resolution for that. Let's say that the iterative method is very simple, is that you start first trying to find the first vector to transform that. So it's like, okay, I am in the input space and I'm looking for the first projection, exactly as with PCA, right? For the one that know this technique. So you first find the first line where the projection over that will maximize the correlation score, okay? And once you have that, you are going to add a new direction, so a second line that will, again, ensure you that you maximize the second criterion, right? The same criterion on your second line, sorry. And then, of course, being sure in the same time that you are orthogonal to the first line that you previously find, okay? So you iterate these kind of things and there is no problem. You are able to produce, the whole set of lines that ensure you get the maximization over the correlation score of the output, right? The global optimization is just that, okay, global, because in the first iterated system, you know, I never optimize like the global optimization over all the lines. I start with the first one, okay, so I maximize something with the first one, and then after I'm looking for a second one, a second pair that will maximize the second term and so on, okay? But you can also, of course, rewrite the thing as a global optimization, right? And also by defining the two matrices corresponding to the whole set of vectors that correspond to the projection line that you're looking for each of them, right? You can rewrite the global optimization as a maximization over a trace, okay? A trace over a specific matrix that is the transpose of the matrix of all the first parameter, okay? With, of course, the same matrix I presented before, at least for the, sorry, for the evaluation of this matrix over the data, okay? So that is the expectation, sorry, of the empirical expectation over my data, all right? So it's possible to express all these things, all right? And it's possible to solve. It's just after a question of, I didn't put the exact solution, but it's like, I think I write it something, as you have a matrix decomposition, okay? You have to solve and find eigenvalue for some matrices, and you are able to exhibit the solution, right? Okay, so that means that it's possible thanks to a set of data. So it's data driven. It's very important. Image plus text, similar pairs. I can maximize the correlation score just considering two linear transformation over my whole set of data. Okay. And we can see also that it's we can rewrite the things. It's just interesting when you consider the metric learning point of view I described last course. That's why I put that. Also, there is an equivalence in having some distance between the two sets as the output. So, of course, when I do a correlation score, it's much more related to similarities, so to dot product in my output space, okay? And when I consider distance, it's much more related to some minimization of all the distance, Frobenius distance in that case, because it's in between the whole matrix, okay? And in that case, of course, I minimize that, right? Okay, so there are, yes, so it's interesting techniques, of course. This is the basic way to do things. We have an exact solution, as I said. We can exhibit exact solution. It is kernelizable, right? So you remember when I talk about dot product, I said, okay, we can extend dot product by kernel, right? As soon as we are able to find admissible kernel for our problem. So that means here, when I express my problem, it's everywhere it's with dot product in my output space. Then I can try to put a kernel and to see if everything may be rewrite in the kernel space, so in the dual space corresponding to the kernels, okay? And so it's the case, it has been proved, and I have another optimization in my dual space with alpha beta parameter in that case. And I can exactly do the same thing, so maximize my similarity, but no more in terms of just a dot product, but a kernel product or a dot product in the induced space by my kernel, all right? So this is interesting also because it's more tricky, of course, combination. It's no more just linear, it's kernel-based transformation that I can learn, right? But of course, there are, okay, some difficulty because, as I said, there are exact solution, but it's not. I mean, I can exhibit like where it is. It's more for now. Yes, I can have like a very easily as stochastic a data-based criterion. So I can decompose my whole criterion as a sum of criterion over each of my training data, my training set, so my training pairs. Okay, and then in that case, it's more difficult to do, for instance, SGD or stochastic gradient descent over the whole set. Over each example for the whole set, and then to be able to be very scalable when the data set become very high, very huge data set, right? Okay. All right. So because we are talking about deep, so we want to see how we can extend, not in a term of kernels, but in term of but in term of deep architecture, right? So it has been proposed 2 years ago, all right, and redo or optimize and improve version recently also. And it's a natural extension of what we did to know what I presented just now, right? That is, instead of just doing so, certainly it's also an answer to one question of the last four about how we can combine. So actually they put the, in particular, a canonical correlation analysis on the top. So the last layer is somehow the two matrix that I presented, plus, of course, the optimization of the correlation score, right? But, okay, below, there are two different, of course, in that case, deep architecture, right? So here, it's not Siamese one, as I presented for the images, because, of course, it's not the same kind of data, it's not the same view, so there are really, two different deep net that we have to consider here. Right? Okay, but I would say that it's really, a straight optimization or extension of the CCA. You can still define this maximization of your correlation score at the output, and you have no problem to re-express all the different things here, okay, by just considering that you have this linear transformation on the top, okay, and after, because, and that was also one of the good things of the CCA or criterion, it's differentiable, so you can write like derivative of this gradient over this criterion, and then you can backpropagate by backpropagation your gradient in the two different branches of your deep architecture. Okay, so here, this parameter will contain the last transformation, but also possibly as deep as you want all the parameters that you want to also refine or re-optimize or optimize in your deep net. Okay. All right. So not very complicated things about that. So they put some example typically to show an example. For the image, they use the kind of deep we presented because it's the one with 8 layers, okay? And so, of course, what people do time after time is to replace, the first dip of Krzyzewski by second dip of Overfit, and then by the new dip of VGG or the Google one, okay? So the Google Net, if you want, and also that will be the same thing for the texture, for the text feature. You can have different proposition here, right? And I'm going to now to go more about this how to represent the text in the next approaches. Okay, but basically, once you did that, you are able to really, I mean, like have induce a semantic space. Okay, because you are now able to have one image and all the transformation, like deep transformation plus the linear top transformation in order to get a nice representation in this semantic space. Semantic in the sense that it's also the space for text. So it's like a joint space where you can do the same thing for text. You have like the embedding of the text, and you learn both embedding together to be as nice as possible for similar pairs, right? Thanks to this correlation criteria, right? Okay, so that means typically that the first application is that, okay, I have one image now as a query. So I can compute, so I go through my feed forward and I compute the transformation and the point I can get, find a point in that space. And then I can look around, just look around and see if there are other points, okay? And find if these points are coming from text that have been previously encoded in, for instance, my very large data set, okay? And then I say, okay, it's very close to that image. So it's a good caption, it's a good illustration, it's a good text for that image. Then I can propose this text for captioning this image, right? Okay, so I can describe my image by some text that have been previously processed by my system, okay? Or in the other, of course, on reverse way, you can say, okay, I have a new text. I want one image that may illustrate, for instance, a man scale a rock in a forest. Okay, I'm looking for that. I compute the embedding. I'm looking for images that are close to that one. And then, okay, I propose to the user this illustration corresponding, if everything is correct, to interesting image, okay, for my problem, right? So this is typically the idea of the first idea of having this common space is to be able to do retrieval, okay, thanks to that in a very big data set. Right, so they present different, I will come back to more to different results later, but okay, what is important is to say that to evaluate this kind of techniques, so usually you define a recall at K. So that means you can't, okay, so you have one image, for instance, or one text as a query, and you count how many correct image you find in the top K answer that you have, okay? So you go for your space, you find the top K most similar images to your text, you propose that to the system, and when it's evaluation, of course, you know the answer, and so you can count how many are good or not, and of course, as soon as they are good, it's better, right? Okay. So you can compare different techniques. So one point that is not completely, I mean, like explained and necessarily convincing is, of course, this is a criterion. Okay. So is it the best criterion for my problem? I mean, having this kind of correlation and just over similar pairs, right? And of course, people recently, I mean, did a lot of work for having more complex textual representation, right? And to see how also we can mix them together. So here, basically, this is the semantic dependency tree RNN techniques. You still have a convnet for image. So for the embedding, it's a convnet. You have something that is more tricky than the thing I presented in the last slide about the sentence representation, okay? You have like a composition between different points and so on. But at the end, you also have like a more tricky, but an embedding of the text here. And you have to define a similarity between these images, of course, and to define also how to learn them, okay? And of course, differently as I presented before, because they do not want to optimize a CCA correlation score, but they propose, and you should, because you follow the course on metric learning, yeah, you should also mention this kind of things. And typically, you remember, I was talking about having pair training data or triplet for the training data. And you remember that this is really, I mean, like one of the most important message for me to you is that you have to take care about the scenario. This is really, I mean, the way that your data are coming, the way that you are going to put your data to define your constraint over your learning objective function and so on is very important, okay? You still have this thing that is the scenario, the model, of course, so the type of things that you put here, this is the model, okay? And also, of course, the learning by itself. Is it efficient? Is it able to go into the deep? Is it possible to learn all the parameters, not overfitting and so on, okay? But those three things are very important, okay? And usually people forget that the data and the way that you represent the data is very important, right? And so what they propose is different from the previous way to present the data. Is really, I mean, like the triplet loss. You remember I presented on Friday for the metric learning. That is to say, okay, if I take a pair of similar, so one image going through with a text, okay, that I give you, this, of course, that should be closer, that's 2 points, as another point coming from another pair, right? As well for image or for text. So you try to learn how to separate, okay, to make different similar pairs from dissimilar pairs, right? And this is what you have here. So VI will be the image embedding. Y will be, so YJ will be the textual embedding. And typically here, what you have is like a margin-based, with triplet, margin-based criterion, where you say, okay, my similarity for ANG in P is, yes, all the data sets. So I take one of the pair, and then after I choose C that is not in similar as my image I, okay? So this is a similar pair. This is not a similar pair. And then you try to enforce that the similar pair to be much more similar with the gap delta to that one, okay? So the same, okay? So once you have that, you can really, I mean, like, read a lot of paper because most of them are based on this kind, very quickly on this kind of criteria. Okay, and it's the same in the other sense. On the other side, you just take the text as a referent and you put away some non-relevant images, so dissimilar here. Okay? All right, very good. So thanks to that, of course, they are able to be, yes, in terms of experiment, they are, of course, the first method I presented, so the TCA, and so they try to be better on many data sets for many classes and so on, right? Okay, as a remark also, you always have in this kind of technique some implementation detail, and it's also related to the things that Michael mentioned, okay, the different tricks that you can have, regularization, of course, over, or some technique to boost your gradient descent, stochastic gradient descent, Okay, so it's also refer to the first talk of Michael on Monday, last Tuesday, the first one, right? So it's better than KCCA, right, at the end. Of course, the techniques of text embedding is a little bit decrepit, and so they already mentioned that more recent paper use another embedding for the text, for the sentence that could be better. I mean, I'm going to mention after, but a way to embed textual sentences is to use recurrent neural net. So the most famous one is LSTM. I'm going to show example with that, but you can use also like a GRU encoder and decoder or whatever. But basically, all these kind of things for this purpose will produce you one vector, okay, in a space for one sentence or one fragment of sentences, right? Okay. All right, so yes. Okay. So I think this is the last one for this kind of really multimodal and how to put the things into the same joint space. Okay, and I put that one because for me it's interesting things where for the first time, as far as I know, you consider that the matching of the image with a sentence may be not just on the top, so like a combination, but may be in a different way. I mean, of mixing them together. Okay, so I am going to explain that. This is the first point, interesting, and the second point is that once you put them together, so you have this kind of criterion. You are not just stopping. So this is like your common representation of one image and one text. You have like something like an output of a deep net. You can see the things like that, okay? And so it's not a score. You are going again to an MLP in order to get the score. So it's typically the last transformation that was linear in CCA or in the deep CCA presented, you have on the top something like that. Here, actually, on the top, you put MLP. And you get the score, the matching score between them. So you are trying to do somehow non-linear, of course, combination in get not a correlation score, but something that is what we need to optimize to get higher score when they are similar and lower score when they are similar. Right? So it's another way to extend, I mean, like linear correlation between the right? Okay, so for the image, sorry about that. When you see the image, you have the embedding. When you choose the image, still a CNN, okay, and on the top you also put some linear transformation to here, very classical, and then you also have to get the matching score, and the output of the matching score is implemented here, and then you also have like two-layer transformation. Finally, for the matching score, there are several possibilities to do that. But let's say, okay, from the image, you compute like your vector and even some projection again with this new vector. And then here, you see that it's one way, I mean, to combine them together. If you want to consider the whole sentence, one vector, and then to work them together, it's already that as soon as I have like a fragment, a part or something like 3 words here, I'm going to combine with my image. Okay. This includes this term. elementary here, CNN. Okay. But so that means that my image will be combined, okay, with many different fragments of text that I have. Right? So this is one way to do that. When you put the image, and you see you put the image to repeat, and your presentation of the image to be able to embed with the different fragments. And of course, after all the different fragments are put together on the base of the embed to get a final perspective. Okay? So that means that it's somehow much more tricky, but interesting way to put them together. Okay, not only on the top, I transfer, I have several embedding, and then. Okay, and of course, I mean, they define in the paper a way to embed the image there. There are three different ways. This is at the input, or they can embed the image within the middle, or they also can embed the image by concatenating both together. So it's less, I would say, the classical way of doing the combination, but of course, it says that there is a originality of having the multi-linear right? Right, okay. And so for the learning, you see that, again, it's something like a triplet loss where you put together correlated and uncorrelated. And we try here, actually, the triplet, where of course the score is the same, but of course you get the score is more tricky. To get, of course, the relevant score, okay, bigger than irrelevant score with the mark, right? Okay, and so with that technique, when they combine all the things together, they compare with the different type of technique, so they are very good. And sometimes not for all data sets, typically for the last one I mentioned, data set. They are very good. I just would like to mention also the thing that we don't see that here, but this is something very important. You should have to work with it. Usually, there are things that make a huge difference. That if you do not take the really up-to-date, last state-of-the-art net, okay, you will not. You can have a huge gap in performance. Okay, so this is typically when they do, I mean, their technique, but with the overfit that is just the previously version, the state-of-the-art version 2 years ago, and this is the state-of-the-art version of the CNN 1 year ago. So the redneck, 100 layer, okay, but then just changing, okay, the deep, very deep, very deep, okay, web amplified, you can have a huge gap in performance, right? So it's important. Okay, right? So for text embedding in general, image and text embedding in general, and being able to learn kind of yeah. Okay, I see your point. Okay, so yes, we are more or less down. Okay, I'm going just to mention to finish two things: automatic captioning and grounding. Yeah, so 2 examples. Okay, just to finish for today. So automatic captioning, you know what is this? It's you have one image, okay, and the system is giving a caption to you for that image. Okay, so a caption is that, of course, a complete description, I would say, or a nice description or textual description of what is inside your image, right? So it can be, for instance, here, a group of people shopping at an outdoor market, okay? Plus, there are many vegetables at the fruit stand, okay? So this is the neural image capture generator that have been called show and tell. Okay, this is one paper from the Google team, and they did a lot of publicity about that, New York Times and whatever. Okay, at the end it doesn't work, but okay, I'm going to just to see, but the idea is very interesting. So this is a little bit different as what I presented before, because what you want to really optimize here is the generator. Okay. So before I wanted to be able to optimize image representation and text representation together. Okay, in a joint space. Okay. Here I just want to be able to optimize the language generation RNN that I have here. So the machine that produce text, okay, thanks to, of course, biasing this process by image, okay, by input image. All right, so the techniques to do that have been proposed is that, of course, so again, I represent my image by CNN, a deep CNN, so because they are from Google, so they use a GoogleNet. Okay, and you put this vectorial representation as an input of your LSTM. So that is exactly a recurrent neural net that is able to produce, okay, so to generate sentences, right? So you need to learn, of course, this LSTM in order to produce, I mean, to generate nice sentences, okay? So you can learn LSTM without any images, if you want. If you have many different sentences, you can learn this kind of system, right? So I put the equation of the system, I just put the way that, of course, we modify each time to have parameter here, so a matrix to train here. I know, so this is the basic matrix to train for the X, and then this is the LSTM. I have different parameter in my LSTM, okay? This is for long short-term memory, the LSTM, right? Okay, so LSTM, when you have LSTM, the basic way to work is that if you start with one word, right? You are going through the LSTM if you just forget that, okay, at the moment. And then you are able to produce a new word, okay? So the idea is I start my sentence with the first word. I go through the LSTM that have been already learned, okay, with many sentences. And then I am able to produce a probability for any of the words that I have in my vocabulary, okay? And I would say that there are a few techniques to select some of the best, but imagine that if you have one best with a high probability, you are selected actually the second word of your sentence, okay? And this word, when you are in test, you are going to give this word to your LSTM again, okay? And LSTM has, as parameter, has this input, of course, plus, okay, the memory, I would say, that, so he keeps some internal representation of what he saw before, okay? And then, so that means with the two, he keep information about the beginning of the sentence, okay? So once it's learned correctly, he is able to produce a third word that makes sense with the two first that you have, okay? And then thanks that, you iterate the system. And usually LSTM, once it's learned, is able to produce a whole sentence and to stop at the end, okay? And there are specific, I mean, they are able to produce a specific stop word that say, okay, I finished, I'm done, right? So with LSTM, once it's correctly learned, you are able to produce sentences, okay? So what they did, actually, they just put as input of the LSTM, okay, for learning, the image representation. So they add the image representation to their system LSTM. It's like if I bias my system to be able to learn not only from textual information coming here, but also from my image, from an image, okay? And so the idea is after in test, when I start here, I am able to, okay, from one test image to produce, I mean, to bias this LSTM, to start with just to start my sentence, and then to get the next word that should correspond, of course, to the image that you have and to the beginning of the sentence that you want to start. Okay? All right. But finally, okay, so there are many things about learning. I'm going to switch. But the only point is that finally, when we talk, I talk with people from Google about that. Okay, so it seems that the sentence generation is works very well. I mean, like for people from text, is not so crazy to have. It's expected, I would say. Okay, to have this kind of things working well. So what does it mean? It means that when you have to produce, when you produce a sentence, it's correct. There is a beginning, end of the sentence. It makes sense and so on, right? But there is no. It's not very. I mean, interesting. I say that. So it's not very. There is not a very nice correlation in between the image that you have and the sentence that are proposed. Okay. So sometimes it works well, and you can generate many different sentences for one image, and choose one that seems okay, correct. But there is no, I mean, like very nice matching correspondence between the image and the sentence that you produce. Okay, and in other words, it's difficult to really, I mean, not only to interpret, but to go into the way that one image may produce, I mean, the good sentence from this kind of scheme, right? Okay. Okay, so right. Okay, so this is for captioning. I would say that there are, of course, plenty of improvement of thinking about these techniques. In order to be able to better interact between the text part and the image part. Okay, and one way certainly have been to consider that we have to not process the image as a whole. Okay, we have to put somehow sciencey base. So that means that, for instance, when I have this kind of a group of people, I would have to say that certainly the part of the image that makes sense for that is located here. Okay, so I should be able to infer some sciencey detection of a part of the image matching with the part of the text I'm talking about. Okay, something like that. Right, and this is typically the last thing. What is about the last thing I want to talk before concluding my course is about this very nice paper, I think here. Okay, it's my favorite one in the one I presented there and this is exactly related to this question. So very simple of having or not a global representation for the image. Okay, and so the point here is to say that certainly if I have a textual description of the image, so when you consider, perhaps we come back to the first thing, I have this image and this text. Okay, what I can put okay, together? Is there, I mean, like common space, represented text, and image, or other thing? Okay, what they propose is to say it's not whole image and whole text. Okay, it's fragment of text with fragment of image, right? So the idea is to say a tabby cat, again, I don't know why Americans are completely, I mean, crazy about tabby cat, but all right. So tabby cat, the tabby cat is leaning. The idea is to be able, once I start to read that, to say, okay, tabby cat is leaning, it's here. So it's what we call grounding. Grounding the text on the image is to be able to say, okay, this is here, right? On a wooden table, I want to be able to produce that wooden table is referring to this part of the image, okay? With one tool on a laser mouse, okay, laser mouse, okay, I want to be able to detect that this is this part. Black laptop, okay, I want to be able to also align this part of the text, okay, so this fragment with fragment of my image, okay? Right? And of course, if you are able to do that, and plus you are able to have a text generation, okay, generative model for text, okay, you can imagine with a test image, so you just arrive with the image, you are able to produce sentences, right? And once it's produced, you have produced that, you are able to come back and to align fragments on your image, okay? So if you combine this kind of alignment here, grounding here, with generative model for text, you can do this kind of generation plus grounding, right? And so, once you have seen, and you are now an expert of RCNN, you remember RCNN is for detection at the beginning of my talk today. So you have bounded box first, and then you pass through a CNN. This is a very basic way to represent your image, no more as a whole image, but by using some sub-regions, bounding boxes provided by the RCNN, right? And it's over, more or less over, right? But they really, I mean, like, exploit and do the same, exploit the many tools that we have now, okay, and try to combine them in an efficient way. So, so they use that. Of course, this is a CNN inside your RCNN that is pre-trained on ImageNet and fine-tuned for the ImageNet detection challenge. So everything is done, okay. And then you can combine this representation for each of your 20, so you define the best 20 boxes that you have in your image, and you have a representation for each of them, right? And this representation is the size of the CNN representation, and then after you try to align by defining the joint image space size that you want, the dimension of that. For sentence representation, okay, because each of the paper try to have a different recurrent neural net, so they tried a bidirectional neural net, but it basically has the same thing as other. You have to embed your sentence, okay. So the way they embed their sentence is a bidirectional neural net in that case, right? So we don't care on that point here. What is very important is that, okay, exactly as I presented before with the LSTM, you have this kind of encoding for each of the different words that you have in your space, okay? But of course, these words are also link to the other one thanks to the deep recurrent net that you represent, exactly as I explained for the LSTM, right? Okay, and then after it's very easy. You have here, actually for one image, you have the whole image and plus 19 different bounding box representing every boxes provided by the RCNN. Okay, all of them going through the RCNN representation, and then here you have like your VI representation, and you can for 20 VI representation, and you can match with each for each bounding box for every word that you have here. Okay, or fragment, I would say fragment, right? Okay, and then they define a match as a dot product here, and you have to recombine all of them. So you have to define where the best match. So you take a max here. So for each textual fragment, you take the best of all the sub window, and then after you combine by some here. Well, okay, it's an ad hoc way to merge them together. And then you are able to get a score again, okay? And then after, again, you are able to define a cost function to optimize. You do that, you join, you take care about many things for the learning, you have all the tricks that come again. And then you are able to produce many results to compare with everyone. But I would say typically, let me show, here, example about how you can align things. And so in that case, and sometimes you really have this kind of data set where you have images, there's many different things that correspond to objects, for instance, that you have in your image. And then in that case, you can try to ground them, okay? So for instance, they find that there is a woman, men also, okay, so everything is not very nice. Woman in bikini somewhere here, okay, but you also find dog here, okay, you find grass here, so okay. Again, it's not perfect. It's really, ongoing, very recent research project from Google, but this is not from Google that one, sorry. But it's it's still, quite amazing kind of application. Right, and the last one, the last slide. Let me check. Yes, okay. Right, and the last slide also about very funny application that people from computer vision find recently is to do like visual QA. So that means that the idea is that, okay, I give you one image, okay, and there are some demo on internet, of course you can try. So you give one image and you ask for something on that image, and the system has to answer to you, okay? So for instance, you have this image and you can say, okay, how many chairs I have? Yeah, okay. Or it can be, what is behind the table, right? And you ask the system to answer. So the input in that case is one image plus one question, right? So again, it's a little bit, it's a different scenario than the one I presented before with multimodal embedding, but it's not so far, of course. Okay. And so one very, very basic way to do that is that, exactly as I presented before, with LSTM, you are able to train, okay, a system, a machine based on the LSTM to produce the sentence. Okay. So if you have sentences, you can train the system many sentences. You train the system to produce this kind of sentence. Okay. But of course, here I don't want to produce the answer, the question. I want to be able to produce the answer, right? So what you can do is that to consider, because the machine don't care about that you have during the training, of course, the question, but also the answer. You know the answer during the training. Okay? So you can really propose to your LSTM like bigger sentence, okay, that ending after the answer. Okay, not ending after the question. Okay, then you train your LSTM to do that. And so that means that after, if your LSTM will only partially know the whole sentence, because he will have during the test only the part corresponding to the question, he should be able to continue, okay, and then to produce as best as possible the answer, right? Of course, you have to put the image somewhere, okay, otherwise the system will just take your question, not see the image, and produce an answer. Okay? So it could be a problem. All right, so basically what they do is that, okay, I represent my image by CNN, you know that now, and I put the CNN as an input. Okay, I combine my textual representation, this is the vector, I concatenate with my image representation, I go to my LSTM for each part. So it's a little different as I said before, okay, it's not just at the beginning or something like that, it's at the level. All right, and then you are able to do that and to then to really, I mean, you give an image, you ask questions, and the machine answers to you. Okay? And you see the point, of course, to visual create, to try to be as good as human could answer to your question. Right? It doesn't work at all. I have to say that again. So typically, I mean, typically the system when you know, it's a very recent paper. But when they compare the system, they also try to compare without having the image, as I say. And the difference was very, very few between the system having the image in test or not. Okay, so you can imagine that there is, I mean, room for improvement of this kind of things. Right? Okay, so it's in my talk, it's in my course. And so, do you have any question? Any comments? Yeah. Yeah. Hmm? This one, for instance, yeah. Yeah. Of course. Yeah, of course, you're right. Actually, this is not produced only with that. Actually, you keep information each time you have unpooling here. So as soon as it's read, actually it's related to the pooling that you had in the first step. So I would say that special information or geometry, some part of the geometry is contained into these things. So actually, this is only the what of the information, but the where is somewhere, okay, stored in this from which pixel is coming the pooling, the max pooling. Okay, so typically, again, when I take one here, okay, I'm going to unpool, so go over 2 by 2, okay, and the way that I propagate this information, so I want to, if my image is only, I mean, like 3 by 3, so I have to extend each of them, okay, to 2 by 2, okay, so this pixel and the square I have here, I have to decide which one I'm going to put where I'm going to put the value, and to decide, in fact, this information about that this unpooling is coming by the other side, where I decided here that, okay, the pooling was coming from the max. For instance, I know before that the max was coming from that point. So I keep this information, and when I do my unpooling, I put the value here, right? Okay, and that's why I have this kind of things with sparse, of course, because it's 1 against 3 non-zero value, and then after I put somehow some filters to better densely represent the information about the region, and I try to learn this filter in my whole hierarchy in order to be able to produce maps that are very close to the supervised map. Yeah. Yeah. No. No, but okay, what you try to do is that you try to learn filters that may recover the important information that you want not to reconstruct the image, but to be able to produce the right mask for the segmentation problem that you have. Yes, I did some work on reinforcement learning for images. Yes. So there are some things that you can try to when you have for instance, when you have a representation where you have I would say too many different classifiers that can operate together. For instance, if you consider not the whole image but part of the image and you try to classify and so on, you have different schemes to have some hierarchical classification decision, I would say, and then you can represent in a different ways this kind of process, right? That are very like represented like Markovian decision process in order to be able to give a label at the end for your whole image, okay? But you have many different steps for that, and then you are no more able to learn in a very efficient way without considering some reinforcement learning in that process, okay? I think there are also, yes, works considering when you consider scientific data, when you try to do also in that case, because you have scientific data, so you know very well what you want to produce, and then you can also define feedback coming from or let's say this kind of reinforcement gain and benefit for that. But if you consider the last talk of Lequin, for instance, he would say that there are 3 types of learning that can be the unsupervised, the fully supervised, and the reinforcement learning. I mean, the type of learning you can consider, and he considered that the reinforcement learning is not efficient at all, actually, because the reward is a scalar value, right? So we can discuss about that, okay? But the reward is a scalar value. What the classification or fully supervised, the reward, I mean, or the score could be, I mean, as many classes that you have, and for the fully unsupervised, it could be as many pixels as you have in your image. So it could be interesting to look in that way, okay? But this is Lequin, and he's very interesting by unsupervised work. So. Okay. Yeah. You know. Yeah, even that one I think is not very easy. I mean, to compare now for the localization, because if you see the last techniques proposed for the last competition, I mean, it's really, I mean, like very big system with a lot of small tricks, and it seems like very, I mean, like engineering now, I mean, to be able to have a better result. And let's say, for instance, Facebook was second at the competition, but if they have changed and what they did after, I mean, their deep CNN by the ResNet CNN, they would have been the first. And the first use the ResNet actually. So it's not clear for me how if you are not Facebook or Google to have interesting contribution. I mean for this task. I mean exactly this task. But there are plenty of problems with even with segmentation, and that can be, for instance, that when you have a object, a very small object. Okay, this is really, I mean, like a difficult task, or many different objects. That means many classes. Okay, so this there are, I mean, at least many problems that still very open, and we have to we can think to have very nice contribution, even like academic teams, right?
The question is that I remember that when I was there was a paper that was a lot of attention because this was out in the application industry. Essentially, this type of test. Please, a hierarchical Markov field, you try to really model specifically probability of each of the people in a certain class, and then using the conditional probability, etc. But how do you think that those explicitly, in a way, even more elegant than you would use the word? How do you think that those very specific recognitions case of application models articulate
I would say very simply that the deep is coming before. Now, this is, I mean, the basic and on the first paper, also for video from Lequin, the recent paper, I mean, they really put the deep. With the deep, you can get very much more interesting or helpful or efficient feature, pixel feature. I mean, you know, very much more nice feature for each pixel. And then after, you can start this kind of completely, fully connected CRF on the top of the things in order to get to get the best result for segmentation. Okay, so certainly, I mean, I would say that the tricky thing of having a very nice pixel representation linked to the different classes that you have, when you try to do everything explicitly, it's certainly go through a too complicated graphical model to be correctly estimated, even if it's interesting, but okay, and perhaps also we are not sure that this is exactly the best way to model, even graphically, I mean, the way that the things are going, okay? But for sure, if you then replace this kind of being able to combine the probability for each pixel to be in one class to another and so on, and then to produce that and to give that to a CRF on the top, you have a very good combination of them. but that it's still, I would say, one of the questions of CNN when I talk a lot about beyond ImageNet. This is typically how we can combine now what we can produce with a CNN, a deep CNN, or RCNN in order to do some reasoning on the top of that or somewhere about that, and reasoning to be able to do more complex inference than just giving a label or something, or to localize or to combine with other information and so on, right? Okay, so thank you very much for your attention, for coming these 4 courses, and hope it will be it have been interesting for you, and perhaps another time. Thank you.
Thank you very much.